fact, you get something you should know. Does anyone know what happens if we make this set empty? Right, we get the disjoint union because there's no constraints sort of put on these two sets. And you should, I guess you should sort of, I mean, so the coproduct is the universal object, the colimit over just this diagram where you have A and you have B. The pushout is, as defined, the universal object over this diagram. But if you make this the empty set, then you've really not specified any additional information, so it reduces to the coproduct. Okay, so the thing to observe from, say, this diagram, if we start drawing these like a wiring, we'll draw this like a wiring like this that says, so, oh God. Okay, so I'm drawing the left-hand side as this wiring that says these two go to this point, and this, well, these two are connected to this point, and this one's connected to this one. So that's that. The right-hand side is the other thing, and the question is, what happens when you compose these two wirings? Well, everything is connected, so we can redraw it as this wiring. And in fact, the pushout characterized precisely that fact for us. And in general, that's essentially true. Pushouts are, so there's this idea here of sort of considering the relation as a relation, not equivalence relation as a relation in everything, and then taking the transitive closure and then restricting, is approximately captured by the pushout except for one slightly annoying fact, and that is the captured by this pushout. Okay. So what is the, sorry, I just had a mental blank. What is the pushout of these two things? Well, let me draw the other line here. We're going to map this point to this point and this point to where it has to go. And so we've got this point hanging around for free. And so when we take the pushout, we take the disjoint, well, we take the union of these two sets subject to the fact that this point is equal to this point. So we get, again, a two-element set. Now let's translate that into the world of wirings and see whether it says what I wanted. So here's one wiring. Sorry. Oops, it doesn't. So there's another example for a pushout for you. I want it the other way around.
The 2 points inside?
Yeah. I want, okay. So let's compose these wirings, right? What I want to say is that the composite of this wiring, will, when we compose these as wirings, will forget this point in here. But the pushout won't do that for us. So let's construct this pushout. This pushout has 2 points up here. Okay. Yeah, sorry, I got a bit ahead of myself. I needed to change something more complicated. So let's go here. So the new definition is we want to say that a wiring A to B now is, again, a cospan of finite sets. I'm just going to call it a cospan A to N to B, right? But, so, bad definition. So this does not quite capture that, because if we have because of this cospan, say. So what was the rule for turning a wiring into a cospan? Well, we have the input set and we have the output set, and then we have a set of equivalence classes in between. Let's say how we're partitioning these input sets and output sets into groups. All right. But we only put something in what I call here B, but what I'll now change to N. We only put something in here if it represented an equivalence class, and equivalence classes can't be empty. So the point is that everything from here, everything in here must be hit by one of the inputs or the outputs, right? One of the things in the boundary. And so this is not a wiring until, so now it's going to be a good definition, such that if we call this F and we call this G, then we know we can take this object F plus A plus B, the disjoint union, and there's this map called the co-pairing, which was too hard to read earlier. So we've got this map, and what I've just said is that, so this is sort of in brackets, such that this map is surjective.
So you want everything in N to be hit by something in A or something in B.
So, okay, is that clear to everyone?
What is the problem of having wires in the middle?
It just doesn't faithfully capture what we wanted to capture.
It would still give you the connectivity pattern.
It will give you the connectivity pattern, but say if you sort of composed some big diagram of things, and eventually, I don't know, there was just a lot of stuff stuck in the middle that never ended up being connected to anything. When you compose these, you kind of just want the, so you want this, I guess this was meant to be in blue. You want this to look like 2 inputs, 2 outputs, and they're all connected. Right? But if you have a composition, if you model it with a way that has a composition rule that keeps track of this stuff that's not connected to anything, then you end up with this thing plus 3 extra points lying around. And if you do that enough, you just end up remembering a whole lot of points that aren't connected to the exterior, and so you really don't want to remember them. It's just a waste of memory.
It's like junk DNA.
Yeah. Fun.
But less useful.
Yeah. Okay. So we sort of know how to compose. Well, one of the problems with this composing wiring, so we sort of know how to compose wirings, which are these, what I'm going to call joint, I'm just going to call them epic cospans. So epi is another name for surjective, also coming from French. And we sort of know how to compose these things. We said we're going to compose them as cospans because cospans have this idea of taking a transitive closure. But the problem is, even if you start with cospans that are epic, I can say surjective. Even if you start with cospans that are surjective and you compose them via pushout, you end up sometimes arriving at cospans that are not surjective. So you need to find some way of also talking about surjectivity. So the composition will be 2 steps. First, you take push out, and then you restrict to the surjective part, or you throw out the junk. Right? And I'll abbreviate this, but the main idea is that throwing out junk is not too hard to state in the world of functions. Right? So these things turn into some sort of function. And if there's junk around, how do we say we throw it out? Well, the point is that this factorizes into an image, and then we include the image into the codomain. So what we want to do is we want to take some arbitrary function and then factorize it into what we see here to be a surjective part, which I'm writing E for epi, and injective part, which I'm writing M for mono, or monomorphism. And in fact, this factorization is unique up to unique isomorphism. It obeys its own universal property. So there's this thing called a factorization system, which expresses this universal property, and which sort of surjections and injections are formed in the category of sets. And so there's this concept called a correlation, which is dual to the relations that we sort of discussed last time, and you may know well from set theory and logic, that can be defined whenever you have colimits in the factorization system. So some definition says if C is a category with finite colimits, if C has an initial object and pushouts, which is enough, and a factorization system so some sort of thing where we can decompose it into epis and monos, or surjections and injections, that again, as you've seen by now, whenever you introduce a bunch of different structure, you have to say it coheres, so that obey a coherence axiom, which make the factorization system behave nicely with the pushouts or the colimits. Then we can define a symmetric monodal category which I'm going to call co-rel sub C with objects, the objects of C, and morphisms cospan. Cospans that obey this condition. So A plus B to N. So factorization system. Okay. So factorization system En such that A plus B to N, this copair exists in this side. So we think of this factorization system as comprising 2 parts. The first part, which is the first factor is some category E. So here it's the category of surjections, and then you have a category of injections. And what we're saying, just as for wirings, is that we have morphisms being cospans in some category, such that when we take the copair, they're surjective, or this generalized analog of surjective. Okay, so how does this work for wirings? Wirings turn out to be go back over here.
Do you want to say what this monoidal product is?
Yes. I guess this fact is more a proposition than a definition, because I haven't given you all the details. But, okay. So, an example is that wirings are Corel fin set. So this is the category for finite sets. So the objects are finite sets and the morphisms are functions. So again, our objects are finite sets, as we saw. Our morphisms are exactly this definition. Okay, so composition is, in these correlation categories, is given by push out, then factorization, and then the monoidal product is given by coproduct. So what does that mean? We saw coproduct was the disjoint union. So if we have two wirings, so let me here's one wiring drawn as a cospan. Here's another wiring. Well, we can obtain a wiring just by forgetting this pluses here. This thing also happens to be a cospan. Kind of visually, it's obvious. So that gives us a monoidal product. And in fact, this is symmetric because we have a wiring that goes like this, where we have two sets and we just kind of cross them over. So this kind of idea generalizes to the symmetry. So that got abstract rather fast, but the key point is that we've taken this idea of a transitive closure and then restricting and things like that, and recast it in terms of things that have universal properties. And this allows us to reinterpret the structure in any case where these universal properties hold. So we can pick it, well, I mean, we can try to define the structure in any category, but we find we don't have much luck.